This is an iHeart podcast. Guaranteed human.
Work can be a little weird. Cringy training seminars, coworkers who won't stop talking about their plant, forgetting the mute button at an inopportune moment. We have to deal with a lot on any given workday. Sometimes it can feel hard to thrive and move forward in your career. Well, that's where LinkedIn comes in. LinkedIn helps you get ideas and insights from experts in your field, connect with people professionally, grow your network, and access tools designed to help you find the right fit for your next role. Whether you're just getting started, figuring out your next move, or looking to accelerate your career, LinkedIn is built to support you at every stage because LinkedIn is the network that works for you. Visit linkedin.com/knowstuff to learn more.
If audiobooks are your thing and you've been meaning to listen to more of them, you should check out a podcast called Earsay, the Audible and iHeart Audio Club, hosted by Cal Penn. Each episode spotlights standout audiobooks on Audible across all kinds of genres: sci-fi, comedy, romance, thrillers, and more, with Cal talking to guests who help break down what makes each story worth listening to. It's a fun, easy way to discover your next great audiobook. Check out Earsay on the iHeartRadio app, Apple Podcasts, or wherever you get your podcasts. Cue Josh Trumpet. You know what that means, everybody. We are going back on tour again. We are hitting the road next year in January for our annual Pacific Northwest and Northern California swing. And we will be at the Paramount Theater in Seattle on January 24th, Revolution Hall in Portland on the 25th, and our home away from home at San Francisco Sketchfest on January 26th.
Yeah, we'll be at the Sidney Goldstein Theater again, everybody.
A great place.
That's right. If you want tickets and information, you can go to linktree/SYSK, and it's got all that jam. You can go to our website, stuffyoushouldknow.com. It's got all that jam. And we will see all of you guys in January with bells on.
Welcome to Stuff You Should Know, a production of iHeartRadio.
And welcome to the podcast. I'm Josh, and there's Chuck, and Jerry's here too. And this is the We'll Get Through It edition of Stuff You Should Know about the periodic table.
I have other names for it.
Yeah, I'll bet you do. Can you say any of them?
This is the Only Time I Hate My Job edition.
No.
This is the Now We Can Stop Talking About the Sun episode.
Maybe.
Edition. And this is the, my God, why do we ever do episodes on chemistry edition? I failed chemistry. It's the only thing I've ever failed was chemistry.
I don't think I even ever took chemistry, to tell you the truth.
Hey, you didn't fail it.
Right. You can't fail if you don't try.
Yeah.
That's my motto. Here's what I figured out about this. Like driving myself mad trying to learn this stuff and understand it. There is a lot of people out there who have written articles and explainers on the stuff that we're going to talk about who literally don't know what they're talking about. And yet they're presenting their information like they do. And it's wrong, and it's you can't understand it. Or in cases where you can understand it, it still doesn't fully answer the question. There's a lot of stuff out there like that on this, especially as it gets more and more like arcane, right?
Yeah.
There's a whole group of people out there, chemists, molecular chemists, physicists, who understand this, but you can put them all together and they can't coherently explain any of it to anybody else. They can just talk to one another like this. Where we are, where us and everybody listening to this episode right now is stuck in the middle.
Yeah.
We know enough that we can notice when somebody is wrong or not correct or doesn't know what they're talking about, but we don't know enough to understand what the actual scientists are saying and then come back and explain it. So, first of all, Breton cap off to Livia for helping us with this one.
Boy, Livia should get a bonus for this one, quite frankly.
For sure. And then second, we might have to edit that out. We'll have to check the budget. Secondly, we're smart enough to get all this across. We are. But we're also transparent enough to admit when we're like, we don't understand this part.
Yeah, I mean, there's a few parts I still don't get. I imagine the good news is I imagine that maybe about 20% of our listenership is even hearing this right now.
I hope more than that because it's really interesting stuff.
Would you click on something called how the periodic table works?
Well, we're going to have to come up with something else. I think we'll call this one legs, legs, legs.
Colon, tiny lettering, periodic table.
Exactly.
The sex episode.
Right. We'll see. We'll trick them into listening to it.
All right. I know I can get some of this at the beginning, so if you'll allow me to talk about one of the only parts I understand.
Sure.
All right, great. I'll kick it off because we have to set the stage sort of for pre-periodic table construction, which is to say that late in the 18th century, science was working from the Aristotelian, that is to say Aristotle system,
Sure.
which we've talked about some recently, which is, hey, we got 4 elements: fire, earth, water, and air. And then after that, science became a little more nuanced, and they're like, hey, actually, we think there are more things out there, more building blocks.
Yeah.
And maybe we can distinguish them from one another and categorize them, maybe based on their mass. And this was sort of the scene when in 1804, oddly, an English school teacher who was also a researcher named John Dalton said, all right, things are made up of smaller things. Maybe these, which is not new, like for, ancient cultures were even talking about things being up of smaller things.
Yeah, we talked about Democritus in that episode about things we believe before the scientific method.
Totally. That's exactly where it was. But he said things are made up maybe of like these little tiny indestructible, indivisible atoms. He got a lot of that wrong, but one thing he got right was the idea that no two elements that we know about so far, which were not very many at all, at that point, can have an identical mass, and all the atoms of that element have the same mass, which also wasn't quite right, but at the time, it was right.
Yeah, because you got to give it up to these guys. When we're like analyzing elements and atoms and stuff today, we're using like spectrometry and particle accelerators and doing all sorts of amazing stuff. These guys are like burning things. This
is 1804.
Boiling them in acid. Yeah, they were doing all the stuff that a high school chemistry teacher does to demonstrate chemistry. That's what they were doing to actually isolate elements and like weigh them. They were weighing things like oxygen. Like they figured out that if you take a liter of oxygen, you will find that it weighs 1.5 grams. No matter where in the world you weigh it, it's going to weigh 1.5 grams. Like, that's what these people are doing. Can you capture a liter of oxygen? I can't.
I can't.
So, I mean, like, what they were doing was the hardcore, like, bloody, roll up your sleeves kind of chemistry.
Yeah.
Apparently it was like one of the biggest scientific pushes of the 19th century was identifying elements. And John Dalton was the first to say, hey, some of these, I think we can kind of like try to organize them a little bit. And Dalton didn't discover any elements from what I understand. He was just the first one to come up with atomic theory in the modern age and try to start ordering them based on atomic weight.
Yeah, exactly. It wasn't quite the periodic table yet, but it was a precursor for sure. And his very first version in 1803 only had the 5 elements that we knew about at the time: hydrogen, oxygen, nitrogen, carbon, and sulfur. Nitrogen was known as, and I think we said this in the other episode, the azote? Or is it azote?
I guess.
Okay. AZOTE. His second list, just 5 years later, was up to 20 elements. Yes. And then 24 years later, by 1827, that list was up to 36. And as science was progressing, they started noticing patterns, and they started noticing sort of intervals where things would repeat themselves, such that all of a sudden a German chemist named Johann Wolfgang in 1829 said, well, wait a minute, we're noticing these patterns, and some of these things are the same. Like if you look at lithium, sodium, potassium, they have very similar properties, and we can group those together. And those 3 in the modern periodic table are grouped together in the same column. So he was right on the money as far as that idea.
Yeah, and I mean, we as humans are obsessed with finding patterns in things, and like discovering a latent pattern in nature. I mean, there's few things more exciting than that. So these guys were looking for patterns even in places where they didn't necessarily exist, maybe maneuvering things where they should or shouldn't be. Some people took some cracks at it to try to kind of organize these elements by pattern, but they ran into some problems. One was the chemistry wasn't as exact as it needed to be to really organize stuff. There were elements that hadn't been discovered yet, so there were big missing chunks, but they didn't necessarily know there were big missing chunks. But they were on the right track, that you could order these things one way or another, and when you did, they would start showing patterns. Periodicity. Periodic table means that there are periods or patterns that repeat themselves depending on how you organize these elements.
Yeah, and the modern periodic table that we know and loathe. Sorry. I loathe. That thing that they pull down in science class that, teenagers just blankly stare at, not knowing what the heck they're looking at.
But it's pretty.
Sure, if you say so.
Mm-hmm.
We owe that to a Russian chemist named Dmitry Mendeleev. And Mendeleev in 1869 was working on the very first Russian language organic chemistry textbook in 1869 and said, you know what, we have 63 elements at this point. I think we can organize these. And he did so. He arranged things in columns. He had to reorder some things from the previous order. So he's like, maybe we shouldn't organize just by atomic mass. Maybe we should order them into these similarities and how they behave. And the big thing that Mendeleev landed on was leaving gaps where he saw gaps. And instead of just, buttoning it up and making it look a certain way, he said, I'm going to leave a gap here. And this is actually what kind of proved his worth and the fact that he was really on the right track, because in the 15 years following him leaving those gaps, 3 elements were discovered that fit those very gaps that he had left perfectly, like a little puzzle piece.
It's like the molecular chemistry version of Babe Ruth calling his shot.
Yeah, basically.
Essentially. So like when it turned out in the next 15 years, they found those elements that did not only fill those spots, but they had properties that Mendeleev predicted they would. Like he was, like they were like, you did really good, guy. He also predicted some other ones that didn't come true, but everybody was just like, whatever, it's fine. So that was like the model that everybody used from that point on. And it's the classic model that we see today, where it's kind of like a castle with turrets on either side and, the brick in the middle. And then there's like a couple of rows below that are a moat if you squint hard enough.
Yeah.
That's Mendeleev who came up with that whole thing. And the way that they're arranged is not by atomic mass, but by atomic number. That's why if you look, and we should probably say the way you read the periodic table is from left to right and top to bottom, right? So the whole thing starts in the top left with number 1, hydrogen. And the reason it's number 1 is because it has one proton.
Best.
That's right. It has 1 proton, Chuck. And because it has 1 proton in its stable form, it has 1 electron. And all that's going to be important in a minute.
That's right. Should we go ahead and take a break? I feel like that was kind of good setup material.
Sure.
All right, we'll take a break and we'll be right back with more things to enlighten you and numb you.
Have you ever invested in something that seemed incredible at first but didn't live up to the hype? Well, marketers know that feeling. They optimize for the numbers that look great, impressions, reach, and reacts. But when they don't show revenue, well, that's a not so great conversation with the CFO. LinkedIn has a word for that: bull spend.
That's right, because you need to invest in what looks good to your CFO. LinkedIn Ads generates the highest ROAS, 121% of all major ad networks. You can reach the right buyers with LinkedIn Ads, and you can target by company, industry, job title, and more.
So cut the bull spend. Advertise on LinkedIn, the network that works for you. Spend $250 on your first campaign on LinkedIn Ads and get a $250 credit for the next one. Just go to linkedin.com/SYSK. That's linkedin.com/SYSK. Terms and conditions apply. Hey everybody, we're here to talk to you about Wayfair. who believes that spaces should be functional, they should be comfortable, they should be well-designed, and they can be well-designed by you with their help.
Your updated space should feel more comfortable, inviting, and practical for everyday use. And we're talking about outdoor seating. We're talking about grills. We're talking about major appliances. If you need storage solutions, Wayfair can help you out. Patio lighting, rugs, decor. It is your one-stop shop for home.
Yeah. I mean, it's getting nice out, so it's time to think about living outdoors for the next few months. And Wayfair knows that outdoor furniture, it's heavy, it's intimidating to assemble. So Wayfair has stepped in and said, we're going to handle the hard part so you don't have to.
That's right. You can shop Wayfair Verified, your shortcut to the good stuff. And that means their team of product specialists are going to vet everything by hand using a 10-point inspection, testing things like, quality materials, functionality, and features, and even how long it takes to build that piece of furniture. And the overall experience save time, reduce hassle, and improved convenience.
Patio season is here, and these deals won't last. So head to wayfair.com right now to get your outdoor space ready for way less. That's WAYFAIR.com.
Wayfair, every style, every home.
Introducing the all-new Mazda CX-5, featuring more connection.
Hey Google, where's the nearest Pilates class?
Safety that has your back. More discovery on the scenic routes. More passion in the details. And more control in changing weather. The all-new Mazda CX-5. More to move every side of you. See it in 5 films at MazdaUSA.com/5sides.
Google is a trademark of Google LLC. Sequences shortened and simulated.
All right, so the modern periodic table, I think, where was Mendeleev? He had 63 on his first. Yeah, 63 known elements at the time on his first stab. The modern periodic table right now stands at 118, and I think they've already said they think possibly maybe one day it may top out at 173.
We'll see.
We'll see, but that's sort of, the thinking, the logic. But right now we're at 118 elements that we know about. It includes on the chart the name of the element. They're usually a 1 or 2 letter symbol, which is almost always short for the name. But in a case of gold, like when you see AU for gold, and you're like, what the heck is that all about? That just means it's based on the original Latin for gold,
right?
Aurum. And they are placed, like you said before the break, in order of their atomic number, which represents the protons in each atom, and that is what makes that each element unique over those 7 rows, aka periods, and 18 numbered columns, aka groups.
Yeah. So the rows across horizontally, those are the periods. And like you said, it's really important to remember, if you take a proton and add it to an element, you don't have like a variation on the element. You have an entirely new element. Everything else you can mess around with, fudge, mess with the neutrons, mess with the electrons. If you add a proton or take away a proton, you got a totally different element, which is why you can order them by their atomic number. Number 1 with hydrogen, number 2 helium, which has 2 protons, and so on and so forth. When you see that little number in the top left of the square for that element, that's how many protons it has. But again, as we'll see, if we're talking about on the periodic table stable atoms, that means that they don't have an electric charge, they're neutral, and that means that they have an even number of protons and electrons. Protons are positively charged, electrons are negatively charged, and if you have 1 and 1, they cancel each other out. 2 and 2, they cancel each other out. Or at the very least, they make the electric charge neutral.
All right. So if you're looking, if you've brought up a picture by now of the periodic table because you really want to follow along.
Yeah, that's a good idea. All,
God bless you for doing such a thing. And secondly, you might say, well, wait a minute, Chuck. What's that thing underneath everything? We'll get to this in a minute, but those 14 short columns underneath is called the F block. And those are the 7th and 8th periods, aka rows, that are detached, and those are unnumbered rows, whereas the other rows are numbered through 18. So put a pin in the F block. All elements within a period, and again, that is the row if you're looking horizontal, all the elements on each row have the same number of electron shells. And when you think about that in your mind's eye, you're probably picturing how we think of that in our mind's eye because of chemistry class and science class, which is, a circle around an atom's nucleus that holds electrons.
Right, like an orbit. That's Niels Bohr's contribution, although he made plenty of contributions, but the whole idea that we have of the atom being consisting of like a nucleus that's kind of like the sun and electrons orbiting around it like planets, that's thanks to Niels Bohr. And the actual orbit, let's say you have just one circle around the nucleus, that's a shell. It's one shell. Add another one, that's the second shell. Add another one, that's the third shell. And they actually fill up in order. So when you follow along across the rows, the horizontal rows called periods on the periodic table, all of those in that row have the same number of shells. One shell, and the second shell, and the third shell, and the fourth shell. And as you go down, each row has all of the shells that the ones above it had, and now they've added another shell because their other shells are full of electrons.
Right. So if you look at the periodic table, get out your little picture, and you look at that first row or period, that means it just has one shell capable of holding up to 2 electrons. And so that's why there are only 2 elements there. Hydrogen usually has 1 electron, and helium, which normally has 2. And then you go down from there, the second and third shells can hold up to 8 electrons. So those second and third rows are each going to have 8 elements, and so on. For the fourth and fifth, it's 18. The sixth and seventh hold 32. And so there are 32 elements on the sixth and seventh rows.
Just to demonstrate a little further, so helium has 2 electrons in that one shell. Helium's full. The first element on the next row that has a second shell, that's lithium. Lithium has 2 electrons in its first shell. That's full, but it has an extra electron, so now it's added another shell, the second shell, to house that first electron. And you go all the way down to the very end of that row that lithium starts, and you find neon. And neon has 10. Its first shell of 2 is full of electrons. Its second shell that can hold up to 8 is full, so it has 10 total electrons. This is what the periods are showing us, the number of shells, and then eventually in a second we'll know the number of electrons that can fill those shells.
That's right. And the periods of the rows. We're going to say that 1,000 times. Groups are columns, periods are rows, because if there's one takeaway from this whole thing,
Right?
You can at least look smart. And when you walk into a room with a periodic table chart and someone says, what are those rows and columns? And you can say, do you mean groups and periods?
Yeah, and then really quickly after that, look at your watch and be like, look at the time, I'm late, and run out of the room so that there's no follow-up questions.
Yeah, and make a U-shaped hole in the wall. Not the letter U, but a Y-O-U shaped.
Yeah, nice.
Did that come through?
Sure. It did once you spell it.
The groups are what we're going to talk about next, and those are the columns. And this is where Mendeleev realized these patterns were coming into play. And once, subatomic theory came about and we started being able to drill down further and further, we started to be able to get way more specific.
Yeah.
So these patterns and these rhythms on the columns are based on the number of valence electrons for each element, which means how many electrons you would normally find in that outermost shell.
Yeah, and the outermost shell is important, Chuck, because that's where all the action happens. That's when atoms bond together to make new molecules. That's where the attraction or repulsion happens. Like that's the active shell. All the other shells are full. And when a shell is full, it's basically content. It just wants to sit there. It wants to be left alone. But if that outermost shell isn't full, then it's ready for some action. It's got its leather jacket on. It's got its dice in its pocket, maybe a switchblade, and it's looking for trouble.
Yeah.
So more than I think even rows, like all of the elements that are in a row, remember horizontal across a period, they're related because they all have the same shell, the same number of shells, 1, 2, 3, 4, and so on. The groups up and down the columns, they're more related really because they have the same number of electrons in that outermost shell. They can have a bunch of different numbers of shells. Like for example, I think fluorine can have 5 shells, but only 1 electron in that outermost shell. Or it could have 1 shell and just have 1 electron in that outermost shell, like hydrogen. And they're more related because they'll react to other things more than they would if they had different numbers of electrons.
Yeah, we can add something to something you should remember, because this will make you look even one step smarter before you run out of the room through the wall.
Mm-hmm.
Just say, oh yeah, it's organized into periods and groups, and the periods of the rows and the groups of the columns. And if you ask me, the columns, aka groups, that's really where it's at.
They're more related.
They're more related. And then you run through the wall.
Right. So let me give you an example here, okay?
All right. This is if you want to really, really, really be smart. You remember this.
Right. If you have your periodic table out, really honestly, it will make this whole thing so much easier. But if you look all the way down to the second group from the right that starts with fluorine,
yeah.
If you look at fluorine, it has, I think, 9 electrons, and it's in period 2. So we know that it has 2 shells. So we know that it has 2 electrons in its first shell. So it must have 7 electrons in its extra shell, or its second shell. And since we know that the second shell can hold 8, there's one little irritating gap, and it wants to fill it. So fluorine is super duper reactive. On the other hand, you've got things like potassium. It has only 1 electron in its outermost shell, and it wants to actually get rid of that electron, because I think I said earlier, when a shell is full, the atom is content and happy. It doesn't want to do anything with anybody. If it just has 1 left over, like 1 hole or 1 electron, it either wants to get rid of that 1 electron so that it can lose that shell and go down to the next shell, which is full, or it can fill its shell like fluorine wants to with an extra electron. Either way, they're super reactive. And it all happens in that outermost shell, the valence shell, and that's where all that action happens.
Yeah, and you know what? Something we haven't even said that I think is important that dawned on me.
What?
Is the periodic table isn't just a, let's just do this thing so we can group them together. The periodic table is made and it's organized this way so chemists and people that really know what they're doing can look at a poster on a wall at any of those squares and know, because of where it is on the row, where it is on the column, what color it is, and what block it is, and we'll get to those things in a minute. And they can know a lot of very specific things just because of where it sits and what it looks like and what color it is.
Yeah, they can tell you whether it's going to blow up in water,
exactly.
I guess apparently pure sodium does. They can tell you if it's shiny. There's all of this has to do just almost entirely with the number of electrons it has in its outermost shell. All that stuff.
Yeah.
And that's the evolution of the periodic table. People notice properties, physical properties, they noticed appearance, stuff like that. And then as they learned more and more about the atom, they figured out why in the atom those properties existed. And they were able to classify those things together in the periodic table. So like you said, a chemist today can look at that and be like, oh, that's going to be a shiny metal that'll explode in your hand if you look at it wrong because it's in this group of elements, right? And I saw it described by a chemist really well. If you, to a chemist, a periodic table looks like a map to us. Like if you look at a map of the United States, you know that if you are looking at someplace in the north, it's going to be colder there than, say, somewhere in the south. You don't know exactly what the temperature is or anything like that necessarily, but you know generally based on this map. It's a map to the elements.
Yeah, and it also might, you might think if you're looking at a map of the South, like that's where people are more like this. And in the Midwest, people maybe, it tells you, a map tells you a lot more than just like what the weather's like.
Yeah.
Just like a periodic table. So if a scientist, if a chemist looks at silicon, I look at it and I see a capital S, lowercase I, the word silicon, the number 14 in the left-hand corner, and that it's yellow. A chemist looks at it and says, well, I see it's in between on the row, aluminum and phosphorus, and in the column, it's below carbon and above germanium, and I see its number is 14, and it's yellow, which means it's a metalloid. So I can tell you like these 12 things about silicon just because of where it sits on that map.
Yes.
It's pretty amazing. I don't get it, but it's amazing.
Right. I was just going to say, we're not going to explain what those 14 things are because they're the kind of things you have to go to graduate school in chemistry to truly understand. It's okay that we don't understand it. All you have to take away from this, and all we're trying to get across, is that trained chemists can look at the periodic table and realize a lot about whatever element they're looking at and figure out how to mix it with other elements to do amazing things. Or if you put together these two things, this is probably the reaction that you're going to have.
Yeah, and it's also, for someone like us, it can get really confusing because when you look at different periodic tables, one thing you'll notice is that the colors may be different. Like there is no, unless I'm wrong, there isn't one completely settled, this is the only way to do it periodic table.
Oh, no.
As far as a lot of it goes, but like, depending on who you are and how you want to organize the periodic table that you use, those colors may mean different things. So it can get really, really confusing.
Oh, yeah.
When it comes to that stuff.
For sure. And usually there is like a key or a legend on the periodic table that says this is what these colors mean. But if you take away the colors, the layout of them across and down, if you look at a periodic table, it's generally going to be the same for any periodic table that looks even roughly like what you're looking at. It's the colors that really kind of change things up. But more and more, as we've learned more about the atom, starting in the early 20th century onward, and quantum mechanics kind of became a thing, that got incorporated into the periodic table as well. And that is where we get to essentially the third way that the whole thing's organized, which is by blocks, subshells, S, P, D, and F. And so
take it away.
the number of shells that an element has, that's its period across. The number of electrons in its outermost shell, that's its group. The blocks describe where that outermost electron is. And if you'll allow me for a second to just kind of take a little divergence here, it helps you understand it, I think.
Please, can we talk about baseball?
No, not that kind of divergence, like deeper into chemistry kind of divergence.
Okay, I'm going to go out and think about baseball.
Okay, so that whole model that Niels Bohr gave us of like the planetoid nucleus and the sun-like nucleus and the planetoid electron orbiting it, that is really off. That's not at all what they're like. It's good for people who don't really care about this kind of thing to walk around thinking, but when you actually start to try to understand the periodic table, it really gets in the way. So if you can kind of throw that out and instead think of electrons as not particles like planetoids, they're actually waves of energy, right? And they like to orbit atoms because their negative electrical charge is attracted to the positive electrical charge of the protons. That's why they're orbiting or flying around that nucleus. But they don't do it in like these tight little orbits like a planet does around like the sun. Instead, they inhabit three-dimensional areas that follow predictable shapes depending on the energy level of that electron. You can say what shape it's going to follow around that nucleus, but you can't say where it is at any given point in time, thanks to our friend Heisenberg's uncertainty principle. Heisenberg said you can know the velocity of an object or you can know the location of a quantum object. You can't know both. And because we know the energy of an object, we can figure out its velocity, its speed, like an electron, which means we can't know where it is. So these orbits actually are where they may be 90% of the time. That's what an actual electron orbit is. And again, it follows these weird, cool-looking little three-dimensional four-leaf clover shapes, just really neat. And depending on the energy of the electron, it's going to inhabit a specific place 90% of the time around the nucleus of that atom, either close to the atom, further out, depending on the shell that it's associated with. And the block is where the highest energy, the outermost electron, is in that position. And again, it's denoted by S, P, D, and F. And it gets way more arcane than that. But all you have to remember is that when you're looking at blocks, they're talking about the specific location of the most energetic electron. And again, since the outermost electrons are where all the action happens, the most energetic of the outermost electrons are really where the action happens. And that's why it's become a little more sophisticated, a little more refined over time, thanks to the addition of quantum mechanics in our understanding of the atom. Are you there, Chuck? Did you go outside?
Sorry, I just came back in. I didn't actually think about baseball. I was just kidding. I watched an entire baseball game.
Oh, who won?
I have no joke. My brain is too mushy for a joke right now. No, I actually listened to that and I learned from you. So I appreciate that.
Thank you, because I felt like I was hanging from a trapeze by my fingernails.
Well, I was underneath you with a net. That's all I'm good for.
Thanks, buddy. I appreciate it. And by the way, I didn't want to just walk past that's all you're good for. I just couldn't even bring myself to recognize such a dumb thing that was said.
I appreciate that. So the final thing we got to talk about is kind of brings it back to the beginning of how they originally just started to think about grouping things, which was by their atomic mass, the sort of very basic thing that they first thought they could use as a grouping device. And they still will indicate the atomic mass on most periodic tables, but the atomic mass is actually a weighted average of the amount of protons plus neutrons, but it depends on how abundant different isotopes in that element are out in nature, and it's not always the same.
Right.
So carbon is a great example that Livia used. It always has 6 protons, usually has 6 neutrons, but sometimes can have 7 or 8. So instead of having an atomic mass of just 12, 6 plus 6, they take a weighted average and it weighs out to 12.011. So if you see those numbers with a decimal point, you can understand that that's because it's a weighted average and not just a locked-in number.
Yeah, and just it doesn't necessarily have much to do with the periodic table, but you mentioned isotopes, and all those are as an element with more or less electrons than it has when it's stable in a neutral charge. If you take away an electron, it has more positively charged protons than electrons, so that's a positive ion. If you add an electron, like say fluorine wants to do, it has more electrons than protons, so it becomes a negatively charged isotope. So those are possible too, but just bear in mind, you're not changing the number of protons, because if you do that, you have a new element. You're just changing the number of electrons, either adding or taking away. And one of the other things about the periodic table is you can point to different sections and be like, those are the ones that form positive ions because they give away their extra electron. Those are the ones that form negative ions because they attract extra electrons than they normally have in their neutrally charged state. That's another thing that you can just point to at the periodic table.
Pretty amazing.
It is. I mean, the fact that people have figured this out is just hats off to all of the scientists that were involved in this over the years.
Yeah. I say we take a break.
Sure.
And when we come back, we're going to tell you about how things got very interesting in terms of the periodic table in the 1930s, right after this.
Have you ever invested in something that seemed incredible at first but didn't live up to the hype? Well, marketers know that feeling. They optimize for the numbers that look great, impressions, reach, and reacts. But when they don't show revenue, well, that's a not so great conversation with the CFO. LinkedIn has a word for that: bull spend.
That's right, because you need to invest in what looks good to your CFO. LinkedIn Ads generates the highest ROAS, 121% of all major ad networks. You can reach the right buyers with LinkedIn Ads, and you can target by company, industry, job title, and more.
So cut the bull spend. Advertise on LinkedIn, the network that works for you. Spend $250 on your first campaign on LinkedIn Ads and get a $250 credit for the next one. Just go to linkedin.com/SYSK. That's linkedin.com/SYSK. Terms and conditions apply.
Introducing the all-new Mazda CX-5, featuring more connection,
Hey Google, where's the nearest Pilates class?
safety that has your back, more discovery on the scenic routes, more passion in the details, and more control in changing weather. The all-new Mazda CX-5. More to move every side of you. See it in 5 films at mazdausa.com/5sides.
Google is a trademark of Google LLC. Sequences shortened and simulated.
Dell PCs with Intel Inside are built for the moments that matter, for the moments you plan and the ones you don't. Built for the busy days that turn into all-night study sessions, the moment you're working from a cafe and realize every outlet's taken.
Yeah, the times you're deep in your flow and the absolute last thing you need is an auto update throwing off your momentum. That's why Dell builds tech that adapts to the way you actually work. Built with a long-lasting battery so you're not scrambling for the closest outlet, and built-in intelligence that makes updates around your schedule, not in the middle of it.
That's right. They don't build tech just for tech's sake. They build it for you. Find technology built for the way you work at Dell.com/Dell PCs. Built for you.
Chuck, I feel like we made it through the hardest part. We're out of the woods, as it were.
I'm shaking a little less.
I am too.
But I won't fully relax for another 10
Just hang there.
10 to 15 minutes.
Hang in there. We'll get it.
All right. So what happened in the 1930s?
Oh, well, a guy named Dr. Lawrence, I can't remember, but the Lawrence Livermore Laboratory is named after him in part, invented particle accelerators, where you use incredible amounts of energy to throw trillions of particles of different weights or specific weights at a target atom. Tell him how Einstein described this process.
Like shooting birds in the dark in a country where there are only a few birds.
Right. Like the chances of you actually having a collision are so remote that you like they're almost indescribable mathematically. But if you shoot trillions of particles, you really increase your chances of there being some kind of collision. And when you collide one particle, one atom with another atom, with enough energy, they can combine. And when you add proton to proton, remember, you get a new element. And so with particle accelerators, they were able to start creating elements that you can't find in nature. And they started doing this all the way back in the 1930s. And this research is what actually directly led to a nuclear bomb. Apparently, when Einstein heard that Lawrence had created this particle accelerator, he advised FDR to start working on a bomb because it was now a thing. Like the world had just been prepared scientifically for a bomb to exist soon.
Yeah. So lab-created elements, like you said, started being a thing in 1937. Anything past uranium on the chart, you cannot find in nature because it decays much too fast to even be around and know it's a thing and study. But so anything past uranium is lab-created, and in 1937, technetium was the very first blank spot to be filled in with a lab-created element as number 43. Nuclear bombs that you mentioned, when they started doing the nuclear tests out on the Marshall Islands in the 50s, they would send planes out into these explosions with filters on them to scoop up unusual atoms and discover potentially elements. That is how we got element 99, named Einsteinium. And I guess we should talk a little bit about the naming because the IUPAC actually has rules around this. It says new elements have to be named after and this is very interesting, a mineral, a place or a country, a property, or a scientist, or a mythological concept, which is fascinating. So we have some of the latest elements. I believe in 2016 is when we got 113 through 18. We got the element tennessine, because it was there were institutions in Tennessee that led to the discovery of this super heavy element. And so they named it tennessine. And most of them sort of follow that naming convention.
Yeah, nihonium is named after Nihon, which is the Japanese name for Japan. A Muscovian is named after Moscow, where the lab where that was created. And Oganesson,
Yeah.
That's what it is. It's named after a guy named Yuri Oganessian, who is a Russian, essentially element hunter now. He has got tons of funding behind him, has set up new particle accelerators with more and more energy and is bashing things together in the search for entirely new elements that not only don't exist on Earth, they may not exist anywhere else in the universe. They may only exist theoretically until Oganessian manages to smash the right atoms together to create those elements for a picosecond. Like, they're so unstable that they last almost no time at all, which makes them totally useless to us.
Yeah, as of now.
The fact that, like you said, they predicted, I think it's going to go up to 173.
Yeah.
And we're at 100 and what?
18.
Makes people like Oganessian just crazy. Like, they want to find them all. And he actually found a couple of those most recent ones that were inducted, I guess, in the periodic table in 2016.
Yeah. And this is kind of cool, too. Oganessian apparently wanted to name that element Stardust in honor of David Bowie, but it didn't fit the naming criteria.
Oh, yeah?
Yeah.
Too bad. So sad.
Yeah. Too bad. So as far as the sort of the coda on this, Livy is keen to point out that there are gaps in the framework still. There are issues when you look at the periodic table. You needn't only look at the very first one, hydrogen. Mm-hmm. At the far left of the table, it's there because it has that one electron. But it is not like any of the rest of its group because the rest of them are all alkali metals. It's actually more similar to something like chlorine, which is in the second column from the right.
Right.
But, you know, there's still debate on, like, it's not settled on where things should be placed on these various. And there have been, you know, there are alternative tables that people have put out over the years with different tweaks, some small, some large. And it's pretty interesting, I think.
And there's also that 2-period section that's always removed from the rest of the periodic table. It's put down below it. Those 2 sections actually go in.
That's the F block, right?
Yeah. The bottom 2 rows. So they come after, I think, barium, and just go all the way over to, I can't remember the other one. But imagine that the periodic table looked like it did, but then the bottom 2 rows were about twice as long as they are now. It'd look weird. And it's because you would take that lower F block and put it into its proper place if you're arranging these things by atomic number. But the reason why the F block is pulled out is because those 2 rows of elements, the actinides and lanthanides, I think, they might like follow an atomic number in that way, but their properties are totally different from their periods or their groups. And the reason why is because they're the only 2 groups that have the F position subshell filled by an electron, which completely alters their everything. It's just different than all of the other ones. And it's different enough that they just basically removed it until they can figure out where it should sit. Because depending on how you interpret where, like how the periodic table should be laid out, they should go here, or they should go there, or they should just stay out like they are now.
Yeah. There are some, and it's kind of fun to look some of these up if you want to see some kind of cool, at the very least, just aesthetic examples. And then they're not just like, oh, this looks cooler. It makes sense to the person who has put out this whatever alternative or alternate periodic table. Like in 1949, Livia found one from Life magazine that is a spiral, and there are quite a few different spiral or spiralic designs where you have hydrogen at the center, and it's sort of like racetrack shape. If you look at just look up spiral-based periodic chart, and they're very nice to look at. I imagine they're much, much harder to sort of make sense of and read unless you're the person who made it.
Or a chemist.
A chemist would still probably be like, oh, why are you doing it that way?
I liked it the other way.
Or that 3D one that Timothy Stowe came up with that I think physicists are pretty keen on, that has 3 axes of different colors that represent quantum numbers that describe the electrons. But it's, you know, if you look at a 3D version, that's kind of cool too. Mm-hmm. But if you find the traditional one confusing, as a non-chemist, just try looking at any of these other ones. It's really confusing.
Yeah, and it's all it is it's saying, well, actually, no, I think we should arrange them so that they're connected more by this property, like electronegativity, or they're shiny, or they're pretty. I like these elements, and so we're going to put them together. These are my favorite elements. It's just kind of like that, and so you can bend them in all sorts of weird shapes.
Yeah, I have my own periodic table I've designed.
Oh, yeah?
And it is just a big black block, and then Times New Roman and yellow lettering in the middle. It says, "Who gives a S?"
Right. I would have imagined it was a traditional periodic table, but scratched out with a pen almost violently.
No, that's good. I like that better. I'm going to change mine.
I've got one other thing that it has a lot to do with everything, but not anything we're going to go into. But there are some, especially those elements that don't occur in nature and they have to create in particle accelerators. Yeah. But also some that occur in nature, like gold and mercury are two good examples. They have electrons that spin so fast, that are moving at such incredible energies, that they actually are like a significant fraction of the speed of light. That's how fast they're going. And it doesn't matter whether you're talking about like a photon or a planet or a black hole or an electron. Anything that has mass and can move at anything like half the speed of light is going to actually bend time and space. And so for some kinds of elements that have relativistic speeds, meaning their electrons travel close to the speed of light, they have all sorts of freaky-deaky properties. It's why gold is gold. I'm not going to get into that. Just trust me, it's why gold is gold. But also it means that if you could go into those atoms and just kind of exist in them as if they were a universe, you would see that that time and space was bent compared to how time and space exists outside of those atoms, like on our level. That's what atomic scientists have figured out, and it's actually kind of having a mind-breaking effect on the periodic table to an extent.
Amazing.
I think so, too. That's it, Chuck. We did periodic tables. It's done. You did great.
Oh, boy. We don't have to do it again?
No, I don't think so. God, I hope not.
Good.
Yeah.
Oh, good.
What is this, Murphy's Law? Well, since I said Murphy's Law and Chuck laughed because he got the joke, you may not have, and that's okay. That means it's time for listener mail.
All right, I'm going to call this a very quick follow-up from our Halloween episode. As we record this, it is actually Halloween. So that has just come out today. Mm-hmm. And we have something from Owen that perhaps explains something that we kind of wondered about. Hey, guys, once again, loving the yearly Spooktacular. Figured I'd mention my take on what the hermit meant. Hermit meant when he said the man's eyes didn't match his mouth.
Oh, yeah.
I think it might have something to do with honesty, like the words of encouragement were somehow disingenuine. That lined up with the idea that the hermit is sort of seeing flaws and faults. That makes sense to me. Eyes didn't match his mouth.
That's like the best explanation I've heard so far. It's also the only explanation, but it's a good one.
I think that's totally it. And Owen says, regardless of whether that's the author's intent, I'm using the description in a song I'm writing.
Oh, cool.
So thanks for the inspiration. And in all honesty, the voice work is on point this year. That is from Owen.
Thanks a lot, Owen. Here's some inspiration for the musical part of your song. Oh,
no.
If you want to be like Owen and write in to explain something to us, we love that kind of thing. You can put it in an email and send it off to stuffpodcast@iheartradio.com.
Stuff You Should Know is a production of iHeartRadio. For more podcasts from iHeartRadio, visit the iHeartRadio app, Apple Podcasts, or wherever you listen to your favorite shows.
You know, you could be adored by everyone and still completely ignored by your cat. Trust me, I know. But if you feed your cat Sheba, you can go from being ignored to truly adored in 12 days guaranteed or your money back. Sheba has a full menu of products, appetizers, entrees, treats, even a kitten's menu. It's so cute. So Sheba has a product for even the pickiest eater. Like Sheba Puree, it's made with bone broth, their chef-inspired flavors. It's got a smooth and creamy texture that cats love and contains no corn, wheat, soy, or artificial flavors. It's food that your cat's gonna love. To learn more, check out Sheba.com. That's SHEBA.com.
Service opens doors, and at American Military University, it can open doors for the whole family. If you have a loved one who served in the military, you may qualify for reduced tuition. AMU offers flexible online programs designed to fit your schedule, so you can keep moving forward wherever life takes you. Learn more at amu.apus.edu/military. Open doors to the future for you and your family with the help of American Military University.
Introducing the all-new Mazda CX-5, featuring more connection,
Hey Google, where's the nearest Pilates class?
safety that has your back, more discovery on the scenic routes, more passion in the details, and more control in changing weather. The all-new Mazda CX-5, more to move every side of you. See it in 5 films at MazdaUSA.com/5sides.
Google is a trademark of Google LLC. Sequences shortened and simulated.
This is an iHeart podcast. Guaranteed human.